Hello everyone, today we'll be talking about integration in FEA. In finite element, to determine the stiffness matrix or the mass matrix or the stability matrix, we have to find an integral of a function. And sometimes depending on the shape functions or the element type, that integral could be challenging. Especially if we are dealing with nonlinear problems. If we have material nonlinearity, the C matrix would be nonlinear, and if we have geometric nonlinearity, the B matrix would be nonlinear. So the solution to this integral could be challenging. So we need to explore options for numerical approaches to find the integral. Integration by its nature could be challenging. It's very different than derivative of a function. For example, if you want to find the derivative of x times ex, that would be the derivative of the first component times the second component plus the derivative of the second component times the first component. But with integration, you need to find a method to take an integral of this function. Or if you have x, ex, cosine x, it becomes almost impossible to solve it analytically. So we have to resort to some numerical solutions. To find the solution, we can go back to the definition of integral. If we have a function fx, and we want to find it between the interval a and b, the integral would be the area under the curve. So if we find the area under the curve, we can actually find the integral. We have multiple integration methods. We can group them into two different categories. There are equally spaced intervals, like rectangular, midpoint, trapezoidal, and Simson rules. Also variable spaced interval with Gauss-Legendre Quadrature. That's what finite element softwares use for determination of their integral. But all of them are based on the fact that we are going to find the area under the curve. So let's start with the simplest one, the rectangular approach. In rectangular approach, we are just going to approximate the area under the curve by assigning different rectangles. And finding the area of the rectangle is very easy. It's just the base times the height, and the height would be fxi. So the integral fx dx using the rectangular approach would be fxi, the height of a rectangle, times delta x, the base of a rectangle. And delta x would be our limits, the high, the final value, the initial value, divided by the number of divisions. It gives us the base, and all of these rectangles are equally spaced. And xi would be the first point, the second point, the third point, and so forth. So by adding the area of these rectangles, we estimated the area under the curve. So we can think of a better approach to find the area under the curve if we just move the rectangles a little bit. So the height of the rectangle would represent the value of the function at the midpoint, then we get a better estimation. So the height of our rectangle would be our function at the midpoint, at these dot points. So the height would be xi plus delta x over 2. So that's half of our interval. So we are evaluating the function in the middle of our interval, and that would be the height of our rectangle, and delta x would be the base. So this midpoint approach, visually we can see it gives us a better approximation. If you subtract the extra areas from the areas that are missing, we get very close to the exact solution. But better than midpoint is trapezoidal approach. In trapezoidal approach, we know that we can find the area of a trapezoid. So why not use trapezoid for our estimation rather than a triangle? So we can use multiple trapezoid to estimate the area under the curve. To find the area of a trapezoid would be the first height plus the second height times the base divided by 2. The base is delta x here. And that's what we are doing. The base, delta x, times the two heights divided by 2. That's where these two come from. gives us the area of a trapezoid. And then because we have multiple trapezoids, we add them together to find the area under the curve. And that's our trapezoidal approach. The other approach is Simson rules, which deals with a quadratic function. So to estimate the area under the curve, instead of using a rectangle or a trapezoid, we are using a quadratic function. And quadratic function is known by 3 points. So these are our 3 points for the quadratic function. And at the end, we get the Simson rules, which is similar or basically exactly the same as Newton-Cotes third point approach. And that's the equation that we get. You can see that there is a pattern for our equation. Is the first point, the coefficient is 1. The last point, the coefficient is 1. And then you are fluctuating between 4 and 2, 4 and 2. And then that would be the point, the penultimate point, the point before last, and that would be the last point. We can use the Simson approach. But here we are going to talk about a better approach, the approach that we use in FEA, and it's very accurate. So in this approach, first of all, the intervals are not necessarily equally spaced. They could have different bases. And this approach is valid for -1 to 1. So if your integral is not -1 to 1, you have to transfer it to -1 to 1 range before we can apply this approach. And this approach uses weights as sampling points to find the integral. So for here, I'm going to show you a 2-point Gaussian quadrature or Gauss-Legendre quadrature to be accurate. We have 2 sampling points, lambda 1 and lambda 2. These sampling points seem to be random, but actually you can drive the values and find that these are the values that we have to use. We are not going to go through the derivation. There is a table that gives you the sampling points and the weights for each number of Gaussian points. So here we are looking at the 2-point Gaussian. So we need 2 sampling points, and these are the sampling points that I looked up from the table. And for each sampling point, you're going to find the function, the value of the function at the sampling point. So we have 2 rectangles that we have to find. So it's a 2-point Gaussian quadrature. We have to find the 2 rectangle. It's W1 F lambda 1. W1 would be the base, which for our case, the weight for a 2-point Gaussian quadrature is, the weights are 1. So 1 F at the first sampling point. So this will give me the area of the first rectangle, and this is the area of the second rectangle. So this is this area, and this is that area that I just added together. So again, we are finding the area of a rectangle, but the base and the height would be very specific. We find the height at a specific sampling point. Also, the base do not have to be necessarily the same. For a 2-point Gaussian, the base are the same. Both of them are 1. Let's look at the 3-point Gaussian quadrature. So the values that we have here is lambda 1, lambda 2, and lambda 3. These are the sampling points. We have to evaluate our function at these sampling points. So we evaluate our function at this point. That would be the height of the first rectangle. This is the height of the second rectangle, and this is the height of the third rectangle, and we'll multiply it by the base or the weight. We call it the weights. So here we have 3 weights. Again, these values, you can look it up from the table. This is the weight, this is the second weight, and this is the third weight. You can see the weights or the spacing are not the same. They are not equally spaced. The spacing is variable. The second one has higher weight than the other 2. So here is the table that I promised. So this is a table. Depending on the number of Gaussian points that you're going to consider, you're going to get the corresponding weighting factors and sampling points. So I showed you for 2 points and 3 points, but you can find it for 4 and 5. When you are solving using Gaussian quadrature, you need to remember to carry these decimal points because we want to be accurate. We are already simplifying our problem by finding an area of a curvature using rectangles, so we are not going to lose accuracy by rounding up. Especially if you're using MATLAB, it's just a one-time job to add all the values in your code or in your Excel file, then the value that you're going to get at the end will be accurate. So carry all the decimal points that you see here. So the question is that depending on our function, we have to use the corresponding number of points. But how can we determine that? The rule is that if you're using an nth order Gaussian quadrature, you can evaluate 2n minus 1 order polynomial exactly. So what does that mean? That means that if you're using only one Gaussian point, you can use a polynomial of 1, which is basically meaningless. Then Gaussian, if you use two Gaussian points, you can exactly evaluate a polynomial of order 3 and so forth. But we need to remember that we are developing these functions and these numerical approach to find the integral for difficult functions that polynomial are easy to integrate. But this is just a basic rule that is telling you how accurate these Gaussian points can be. So if you have a function ex times cosine x times x2, you need to see which order of polynomial would better fit your function. If it's the fifth order, that means that if you're using 3 Gaussian points, you would get an accurate result. Of course, as always, you have a trade-off between accuracy and computational cost. The higher number of Gaussian points you use, the more accurate you would be, but also your computational cost would go higher. But one thing that we talked about is that matching the limit. If we have a function fx_ab, we want to move it to -1 to 1, then we have to do matching limits. So we are going to go from a function fx from a to b to f lambda from -1 to 1. Let's consider a linear function or linear relation between x and lambda. So we know at lambda -1, our function x is a. So if we plug in lambda -1 into my function, I can find this equation. And similarly for lambda equals 1, then x is b, that's the final value. I find this the equation. Solving the two equations, two unknowns, I can find C0 and C1, my linear equation. If I plug them here, I find x as function of lambda. So that's the important equation that we are going to use when the range of integral is not -1 to 1. And for finding the integral, we also need the relation between dx and d lambda, which is b minus a over 2. You can see here we have dx, we have to find d lambda. So these are the two equations that we are going to use. Let's solve an example. We're going to find an integral of this polynomial function using Gauss quadrature integration. First of all, this is an easy function, so we technically do not need to use any numerical approach. But for practice and because we can find the exact solution, then it's nice to use Gauss quadrature to see how Gauss quadrature is performing for us. But first we need to know how many sampling points do we need to consider. So the required number of Gaussian points, that's the equation that we have. The order of polynomial is 2. Then we can find the number of Gaussian points that we need. So we find 1.5, which means that we need to use 2 Gaussian points. We need to round it up. So if we use 2 Gaussian points, first, because the range of integral for us is 2 to 6, it's not -1 to 1. So we need to do the transform. So x, I find it as function of lambda, which is 4 plus 2 lambda. This is the equation that I talked about in the previous slide. And dx would be 2 d lambda. Now I can transform my integral from x dx to lambda d lambda. So this is a perfect format for using Gauss quadrature. Everything is based on lambda and the range of integral is -1 to 1. I just replace x with 4 plus 2 lambda. 2-point Gauss quadrature says that the weight 1 times the value of the function at the first sampling point plus the second weight times the value of the function at the second sampling point. I know the sampling point for the 2 Gauss quadrature. These are the values that I picked up from the table, 1 and f and the sampling point negative 0.577. I just need to plug in the values into my function, and this is my the whole function is my f lambda, including the value of 2, of course. I just replace the sampling point into my function, and I find the value of integral. If you take the normal approach for integration, you would find the exact result. So the value for Gauss quadrature would be exact. So in FEA, we are using Gauss quadrature to find our integration. We have two methods in FEA in almost every software that you use, whether you use ANSYS, Abacus, or any other FEA software. We have full integration, as the name suggests. We use all the Gaussian points that we need, or reduced integration, which we use less number of Gaussian points. So the first element that you see, it has 4 Gaussian points. So that's an example of full integration. And the second element, we have reduced integration. So from here to here, we have reduced the number of Gaussian points by 1 in every direction. In x direction by 1, in y direction by 1. So we are from 4 Gaussian points to 1 Gaussian point. So let's talk about each integration method. So full integration, it uses all the Gaussian points that it needs. It is more accurate because we are using more integration points, but also it comes with a problem, and that problem is evident when we are talking about the bending of a beam. In bending problem, there are going to be some shear forces created in our model simply because we are using full integration that are not actually present. So we call them spurious shear stresses. So this phenomena is called shear locking or volumetric locking. That's the term that is used in FEA extensively, whether the elements can handle shear locking or not. And this problem with full integration is present only in bending problems. If you're using uniaxial stresses such as tension, compression, or shear loading, you're not going to have that problem. Or if you're going to use one element per thickness, then you're not going to have that locking problem. But let's look at this shear locking to see what actually the problem is. This is the undeformed model that you have under bending. So that's the positive bending that I'm showing you. After deformation, that's the actual deformation. That's what you're going to see in reality, in experiments. You're going to have curved edges on the top that would be under compression, the bottom would be under tension, and the midpoint would be the neutral axis. But what happens in FEA? In FEA, if you're using linear elements, they cannot represent that curved edges. So you're going to have a flat horizontal face here and a flat horizontal face over there. And also, the more important thing is that the lines are not perpendicular to the cross section. That means that there's going to be some shear forces created here to create that non-perpendicular lines, and that shear force is an unreal shear force. In reality, when you have pure bending, you're not going to have any shear force. So this phenomena is called shear locking. That makes our model stiffer. So FEA, by its nature, is overestimating our stiffness. So the stiffness of the model using FEA is already higher than reality, and then using full integration, the model is going to be additionally stiff. So the deflection would be drastically underestimated. To solve the problem, we can either use reduced integration, do not use full integration, so we don't have shear locking problem, or use higher order elements such as quadratic, cubic, so we could actually model that curved edges. Now reduced integration. For reduced integration, you only have 1.4 quadrilateral element. Depending on the element, you're going to have a more number of Gaussian points. But the beauty of reduced integration is twofold. Is that one, you are using less number of Gaussian points, so your analysis is less computationally extensive, and also you're not having the shear locking problem that is present in full integration. So you're not having shear locking. and your stiffness is going to be underestimated using reduced integration. So the stiffness is overestimated by using a finite element and is underestimated when you're using reduced integration, so they're going to balance each other out and you're going to get a better result. So that's very interesting that the simpler approach gives us a more accurate result. That's why in FEA or in ANSYS, reduced integration is the default mode. We are using reduced integration unless we change it manually. Reduced integration also comes with a problem. We call it hourglass mode. Because we don't have enough number of Gaussian points, your stiffness matrix, you might have some zero values in your stiffness matrix. And these zero values are going to create, they're not going to have any resistance to deformation. Therefore, you're going to see drastic deformation if you excite your element or model in the hourglass direction. So in ANSYS or some other FEA models, you would see they give you an option of reduced integration with hourglass control. So they're going to control the hourglass problem. So an hourglass problem is more likely to occur in coarse mesh. So you have the problem of shear locking in reduced integration and an hourglass problem in shear locking in full integration and hourglass in reduced integration. So here I'm showing you beam 189 as an example. I've just taken this image from the ANSYS library. So you can see here the integration points. There are 4 integration points for a beam element, for whether there is a rectangular section or a channel section. But because we are using a full integration, the accuracy of our approximation, our interpolation, is as high as cubic, even though we are using quadratic interpolation, because we are using 2 Gaussian integration points. And in ANSYS APDL, you can change the integration. If you select the element, I've selected plane 182 here. If you click on options, then if you go to element technology, it gives you the choice of whether use full integration or reduce integration, and that's up to you. That's your judgment which integration would be helpful. Each of them are going to give you a set of problems, so it's up to you to decide which one works better for you. The other thing that deals with accuracy of our analysis is H mode versus P mode method. So in H method, it's based on quadratic shape function, and if you want to improve the accuracy, you have to increase your number of elements. So you have to make your mesh finer. In P method, it's based on higher order shape functions like cubic or fourth order. And the advantage is that you can use less number of elements, less number of higher order elements as opposed to higher number of less order elements. In P method, you can assign the degree of accuracy, or we call it the P method. And then there's going to be an adaptive mesh changing the number of elements to, depending on the complexity of the problem, to get convergence. And you don't need to do any manual mesh refinement. Everything is done automatically. But this method is only valid for linear static structural problems. So many software, including ANSYS, had that P method versus H method. But the new release of ANSYS does not have the P method. That has been removed. So if you go to preferences, discipline options, all you can see is H method. And they have removed it. Probably they're working on it, or they've decided that's too complicated to include it. But the interesting thing is that they have kept this section. So my guess is that they're going to bring the P method back. But the concept of H method and P method doesn't change. If you go to another software, you might have P method, or if you're writing your own code, or if you're reading a paper, the concept of H method and P method are present.